Let's take a look at the modulus function. And for a modulus function, it is represented by these two vertical strokes over here. According to the definition of the modulus function, we will first examine what that is within the modulus function. For example, if we examine what is within and realize that whatever that is within this modulus function happen to be bigger or equal to 0, then the modulus function will just leave it as it is. But if you were to examine what is within the modulus function and you realize that it is a negative number, the modulus function will multiply a negative to it to make it into a positive number. For example, if we have a modulus of 3, 3 is a number that is bigger or equal to 0, so the modulus function will leave it as it is. So modulus of 3 is going to be equal to 3. If we were to do a modulus of negative 5 is a negative number. So what the modulus function will do is to multiply by a negative 1 to make it into a positive 5. Of course, if we were to try to do a modulus of 0, it is still going to be equal to 0. Let's take a look at a few more examples to get ourselves even more warm up to the modulus function. So the first one that we are going to look at in this question number 1a is the modulus of negative 12. So for a, we are doing a modulus of negative 12. Negative 12 is a negative number. So we're going to multiply it by a negative to make it into a positive 12. In B, we are looking at the modulus of 4 minus 11 plus modulus of 7 minus 19. So 4 minus 11, this is equal to negative 7, and 7 minus 19, this is equal to negative 12. So what is going to be happening to modulus of negative 7 is going to become 7. The same goes for modulus of negative 12, it will become positive 12. So this is equal to 19. Part C, we have a negative of the modulus of 22 minus 55 plus modulus of 9 minus 3. This negative will just remain as negative, okay, because this exists outside the modulus function, is not going to be affected. So this is going to be negative 33 plus modulus of 6. So what is going to happen to modulus of 33? It is going to become positive 33. 6 is a positive number, so we will just leave it as it is. Negative 33 plus 6, this is equal to negative 27. The modulus function can also exist within an equation. Let's take a look at an example over here. These are two common scenarios where the modulus function exists within an equation. The first example that I gave you here is this. So when we have something that is like this, modulus of x squared plus 3x minus 34 is equal to 6. Please take note, this 6 here is definitely going to be a positive number, right? I mean, it is not just the 6, but the output of a modulus function has to be equal to a positive number. So if you're to be seeing a question where it says that the modulus of, let's say, this is equal to negative 6, there's something wrong with that question. That is why if the modulus of fx is equal to a has to be bigger or equal to 0. So how do we solve for this? How do we find the roots of this equation? According to the modulus function, if you were to examine what that is within the modulus function, where after it goes through the modulus function it becomes 6, there are two possibilities. The first one is when the expression that is within the modulus function happen to be a positive number, then we will leave it as it is. So this is going to be equal to 6. Another possibility will be when the expression that is within this modulus function happen to be a negative number, then what we will need to do is to just add a negative to it. So it is going to be equal to 6 in this way. We will multiply it by a negative to make sure that it becomes overall positive. So that's what we will do if we were to have an equation that is of a format that is similar to this, number 1. The second scenario is, what if we have two modulus and it exists in this way? When, for example, we have a modulus of 2x minus 5 is equal to modulus of x. So when we have two modulus or even more modulus, we can actually try to examine one modulus at a time. So for example, I decide that I'm going to take a look at the left-hand side modulus. So if I were to look at the left-hand side modulus, that means I will look at it based on two possibilities. One is when it is a positive expression, when 2x minus 5 is a positive expression, I'll leave it as it is. Another possibility is when 2x minus 5 happen to be a negative expression. So this is another possibility. So I'll be forming from one equations to now two equations. And now we have to also look at the other modulus function or any of the rest of the modulus function. So for this possible case here, we will also be breaking it up into two other possible scenarios. One is when x is positive. So when x is positive, it will just be like this. Okay, we will just leave x as it is. Another scenario is when x is negative. If x were to be negative, then we will have to multiply x by a negative to make it into a positive number. So it will be 2x minus 5 is equal to negative x. This, again, I'm going to break it up into two possible scenarios. One will be when x is a positive number, or the other scenario will be when x is a negative number. So we will have to multiply by a negative. But if you were to look at these four possible equations that we have formed, do you realize that two of them are actually the same? Okay, some of them are actually the same, not two of them. Like for example, these two, they are actually exactly the same because I can multiply this negative to the left-hand side, I'll get this equation. I'll multiply this negative over to the right-hand side, I'm going to get the same equation. So these two is actually just either this or this. Let me go for this. So these two equations is actually the same. It's just this. And these two, this one and this one, these two, they are also the same because if I were to just, for example, multiply negative throughout this equation, I'm going to be getting this. So these two other equations, in fact, it can boil down to just this one equation, which means that for a scenario that is like this, we can actually rewrite it into either this or this only, which was what I've done here. Let's try it on some actual questions. But before that, okay, let me just show you one more thing. I personally don't go for this as much, but it works, which is since the modulus function is an attempt to just remove the negative from the whatever that is within the modulus function, right? So what if we were to try to square both sides? Because for a question that is like this, for a scenario that is like this, where you have modulus is equal to a modulus, you can actually try to square both sides like this, because the moment when you square it, the negative doesn't matter at all, right? So the modulus, whether there's a modulus inside the square or not, it doesn't matter at all because negative 1 squared is going to be positive. So another attempt is to try to square both sides. Then you will get, for example, for this particular scenario, you're going to get a quadratic equation, and you just solve the quadratic equation. It works too. Okay, but this only works if you are able to square both sides and remove the modulus at the same time. Okay, so to me, I think I will still go for this as my default strategy, and this will be my secondary strategy, just in case something goes wrong with this, then at least I have some fallback. Let's take a look at an example. Let's take a look at question number 2. Okay, let's take a look at this. So in question number 2a, we are looking at the modulus of 2x minus 5 is equal to 25. And according to the modulus function and according to what we have discussed so far, this is like the first example that we look at just now. So what we will do is we will assume that 2x minus 5 can be a positive number, or 2x minus 5 can be negative. So I'll add a negative, I'll multiply it by a negative. I'll get these two equations. So 2x minus 5 is equal to 25 means 2x is equal to 30, so x is equal to 15. As for this, 2x minus 5 is going to be equal to 20, this is going to be negative 25. So 2x is going to be equal to negative 10, x is going to be equal to negative 10, no, this is not negative 10, this is going to be negative 20, so x is going to be equal to negative 10. So we are getting two roots to this equation over here. Let's take a look at another scenario in part B. And in part B, we have a modulus of a quadratic expression, modulus of x squared plus 3x minus 34. This is equal to 6, which means that x squared plus 3x minus 34 can be equal to 6, provided that x squared plus 3x minus 34 happen to be a positive expression, then I will just leave it as it is. Or another possibility is when x squared plus 3x minus 34 happen to be a negative number, then we will add a negative, we will multiply by a negative to it so that we can make it positive. So this is equal to 6. This is actually the example that we looked at just now. So we have two quadratic equations. Let's just try to go through the quadratic equation individually to solve them. So for this, we have a x squared plus 3x minus 40 is equal to 0. Factorizing this, we will get a x plus 8, x minus 5. This is equal to 0. So x is negative 8 or x is 5. As for this, let me just shift everything over to the right hand side. So we have x squared plus 3x minus 34. If I have to shift over to the right hand side, it is going to be plus this 6. So on the right hand side here, I will have a negative 28. 28, this is equal to 0. Factorizing it further, we will have a x plus 7, x minus 4. This is equal to 0, which means that x is equal to negative 7, or x is equal to 4, or x is equal to negative 8, or x is equal to 5. They are all the possible roots to this equation. Let's take a look at another one. Let's take a look at part C. And in part C, we are looking at this. Part C, we have a modulus of 3x minus 2 minus 2x is equal to 0. So we are working on a 3x minus 2 is equal to 2x, which means that 3x minus 2 is equal to 2x, or 3x minus 2 is equal to negative of 2x. So for this, we can actually just solve for x directly. This x is going to be equal to 2. This x is going to be equal to 2 over 5. Easy. Let's take a look at D. D is a little bit interesting. Let's take a look at it. So for D, we have a modulus of 15x squared minus 20 is negative 13x. So again, if I were to just make use of the same idea and deduction that we have discussed, that means it is going to be 15x squared minus 20 is going to be equal to negative 13x, or negative 15x squared minus 20 is equal to negative 13x. Let's try to solve for the two quadratic equations individually. So for this, if I were to move everything over to the left hand side, we have a 15x squared plus 13x minus 20. This is equal to 0. Factorizing this and simplifying it, we have a 3x plus 5 and a 5x minus 4. This is equal to 0, which gives us x to be equal to minus 5 over 3, or x is equal to 4 over 5. As for this, if I were to shift everything over to the right hand side, we have a 15x squared minus 13x minus 20. This is equal to 0. Factorizing this, we have a 3x minus 5 and a 5x plus 4. This is equal to 0. So x is equal to 5 over 3, or x is equal to negative 4 over 5. But hang on a second, because if you were to just put in a bit of effort to analyze the situation, like what we have discussed, if I were to do a modulus to something, what is the output? I will be expecting the output to be a positive number, isn't it? So if you were to look at this, modulus of this is equal to negative 13x. What does this tell me about x? This tells me that x that is here, this x must be a negative number, isn't it? So that it can become a positive number to represent the modulus function that is on the left hand side. That is why if I were to look at my solution, I need to reject some of my solution. For the solution, I'm only going to be accepting numbers that are negative, which means that positive number that is like this, I will have to reject. Positive number that is like this, I will have to reject in order for x, when it is being substituted back into the original equation, it will make the right hand side into a positive number. Let's take a look at another one. Let's take a look at E. So for E, we have a modulus of 2x minus 5 is equal to modulus of x. It is the example that we were looking at just now, but now let's try to solve for it. So if I were to just make use of what we have discussed, then 2x minus 5 is going to be equal to x, or 2x minus 5 is equal to negative x. These are the two possibilities. As for this I'm going to be getting, this is 2x minus 5. Okay, so for this, I am going to be getting x to be equal to, if I have this, x is actually just going to be equal to 5. Okay, this is like really simple. So this x here is going to be equal to 5 over 3. An alternative that we can make use of, okay, it is to square both sides, like what we have discussed. So let's see whether we're going to be getting the same answers, okay? So alternatively, if you were to square both sides, then we are going to do a modulus of 2x minus 5 square is equal to modulus of x. I'm going to square this also. Again, because like what we have discussed, the modulus will not matter anymore if we were to try to square both sides, because the square will also change the negative 1 or positive 1 into just positive 1. So this, we will have a 2x minus 5 square is equal to x squared. Of course, we can expand this and try to simplify this, or if you are just a little bit of like if you're a little bit lazy, which is actually good for this scenario, you can bring both to the left hand side. So this minus 5 squared minus x squared is equal to 0. Then you can factorize it immediately without having to go through that additional round of expansion. So this is a squared minus b squared scenario. So it will be this plus x. Then it will be 2x minus 5 minus x. It will be a plus b, a minus b is equal to 0. So we will have a 3x minus 5, and this is going to be a x minus 5 is equal to 0. And what's our answer? Our answer is 5 over 3 or 5. Okay, we are getting back exactly the same thing. Let's look at one more equation. So that is f. Let's see how we can solve for f. So for f, we are also going to try both the strategies that we have discussed. So we have this 3x plus 7 is equal to modulus of 9x minus 2. So according to what we have discussed, this will be 3x plus 7 is equal to 9x minus 2, or 3x plus 7 is negative of 9x minus 2. So for this over here, we will try to solve for it. If I were to bring this to the right hand side, 9x minus 3x is going to be 6x. Then this is going to be equal to 7 plus 2. This is going to be equal to 9. X is equal to 3 over 2. As for this, if I were to try to solve for it, we are going to be getting a 12x is equal to negative 5. So x is equal to negative 5 over 12. This is if I were to use the first strategy. Will I get the same result if I were to square both sides? It will, but let's still try. So if I were to square both sides, it is going to be 3x plus 7 square is equal to modulus of this square. Modulus of this square is equal to modulus of this square. The modulus doesn't matter anymore, so we can actually just simply write this as this is equal to 19x minus 2. Not 19x, it's just 9x. I'm reading the modulus notation as part of the number. So here we are going to be getting a 9x minus 2 square. Just for like the ease of factorization, the ease of solving this equation's sake, I'm going to move everything to the left hand side to create for myself an a square minus b square scenario. So 13x plus 7 square minus 9x minus 2 square. This is equal to 0. A square minus b square, it will be a plus b, a minus b. So we will have a 13x plus 7 plus 9x minus 2. Then 13x plus 7 minus 9x plus 2. We have these two scenarios. These are equal to 0. And I will be left with this is 13. Oh, why am I writing this as 13? Because this should be 3, right? It should be 3, so it is not 13. Once again, I've misread the modulus notation as part of the number. Okay, that's my fault. So we have this 3x. So this is going to be 12x plus 5. Then this is equal to negative x, then plus 9. This is equal to 0. So x is equal to negative 5 over 12, or for this, x is equal to 3 over 2. We are getting the same set of answers. Can it appear in any other form of equation? Of course, and let's just try one more, okay? What if we have a modulus function that happens within a simultaneous equation scenario? So for example, like this one over here, okay, we have a simultaneous equation. We have a pair of simultaneous equation. The first one is this 2y plus x is equal to 5. The other one is y is equal to modulus of 2 minus x. We will just make use of the same idea, even if it exists within a simultaneous equation. So I'm going to break this up into two other pairs of simultaneous equation. The first pair will be when this plus x is equal to 5 and y is equal to 2 minus x. This will be my first pair of simultaneous equation. My next pair of simultaneous equation will be this. 2y plus x is equal to 5 and y is negative of 2 minus x. Okay, it is the same idea. And I'm going to just solve this as if it is any other simultaneous equation. I'm going to call this equation number 1. I'm going to call this equation number 2. I'm going to attempt to substitute equation number 2 into equation number 1, which will give us a 2 of 2 minus x plus x is equal to 5. Solving for x over here, x is equal to minus 1. Substituting it back into here, y is going to be equal to 2 plus 1, y is going to be equal to 3. As for this, I will call this equation number 3. Let's call this equation number 4. I'm going to substitute equation number 4 into equation number 3, which will be 2 times of negative 2 minus x. Then plus x is equal to 5. Solving for x over here, x is equal to 3. Substituting it back into here, y is equal to negative of 2 minus 3. This is equal to 1. So simultaneous equations, they're going to be solved in a similar way. The next thing that we're going to try to discuss about our modulus function is to see how we can sketch graphs that involve a modulus function. It's actually also pretty easy. You go through a few steps that are like this. The first one is to sketch the graph without the modulus function. Then after that, what you will do is you will try to indicate all the key features of that graph without the modulus function first, as many key features as possible. For example, you can try to indicate the x-intercepts, the x-y-intercept, the stationary points if there were to be any, the endpoints if there were to be any. And then what we'll do is we'll reflect the portion of the graph that is below the x-axis about the x-axis to the positive side of the y-axis. Okay, because what modulus will do is to try to convert whatever that is negative into positive, right? So if I am sketching the graph of y is equal to fx, for example, it is this line over here that represents the graph of y is equal to fx. This is a negative number. So this negative number will go through the modulus function. And once it goes through the modulus function, a negative number will become a positive number. So this will become this will become this. That is why this entire portion that is here will be reflected about the x-axis. Let us try an example. No, let us try a few examples, okay, so that we can understand how the modulus function can be sketched. I'm going to go through these 3 steps as much as possible for the examples that we're going through. So let's try to sketch this A first. So let's take a look at part A. In part A, we are supposed to sketch the graph of y is equal to modulus of half x minus 9 over 4. But what we are going to do is to sketch it without the modulus first. So y is equal to half x minus 9 over 4. The domain that is given to us, the range of values of x that we are supposed to be sketching, is going to be strictly bigger than negative 2, less than or equal to 5. This is a linear line. It is pretty easy to sketch. So let me very quickly get it done here. So we have the y-axis, we have the x-axis, and the line is going to look something like this. Let me do a quick sketch of it. Okay, the line is going to be something like this. This here, the y-intercept is negative 9 over 4. Letting this equal to 0 will get me the x-intercept. The x-intercept here is going to be 9 over 2. It is strictly bigger than negative 2. I'm going to use a hollow dot to represent that it is an endpoint, but it is not including this point. So a hollow dot will do. It is going to be negative 2 that is going to be substituted into here. The corresponding y coordinate is going to be equal to negative 13 over 4. And it is going to be less than or equal to 5. I'm going to use a solid dot to represent an endpoint that is included. So here is going to be 5, substituting 5 back into here is going to get me a 1/4. So this is the graph of y is equal to half x minus 9/4. But what the question wants is for us to sketch the graph of y is equal to the modulus of half x minus 9/4, where x is strictly bigger than -2, less than or equal to 5. So what will happen is the output of this are all represented by the y coordinates. So when the y coordinates are positive, the modulus will not change it at all, which means that if I were to be sketching the graph, this is the y-axis, this is the x-axis, this portion of the graph remains the same. So it is going to be something that is like this. Okay, it remains exactly the same because the y coordinates are positive. The y coordinates which goes through the modulus function here, the values of the y coordinates of this that goes through the function here, modulus function here will not be changed. So here is going to be still 9/2. Here is still going to be 5 and 1/4. But all these are getting negative values. When it goes through the modulus function, they will just become positive values. That is why it is going to be a reflection to the positive y side. So if I were to just do a reflection of it, I'm going to be getting something that is, let's say, like this, where this hollow dot here will be a reflection of this point about the x-axis. The coordinates will be -2 and positive 13/4. Negative 9/4 will become positive 9/4. So this is the graph of y is equal to the modulus of half x minus 9/4. And according to the question, we want to look at the corresponding range of y. So for this, what is the corresponding range of y? Y will be, the smallest possible it can go is 0, and it can be including 0. The largest possible is going to be equal to 13/4, and it is not inclusive of 13/4, so it is strictly less than 13/4. Let's take a look at B. In B, we are going to be sketching another graph, this time a quadratic graph that undergoes a modulus function transformation. So we're going to sketch first the graph without the modulus, which is y is x squared minus 5x plus 6, where x is supposed to be bigger or equal to 1, less than, strictly less than 4. Let's factorize this, and it will be x minus 2, x minus 3. So this is a quadratic graph that is going to look something like this if I were to sketch it. X-axis is here, y-axis is here. I will get a graph that looks something like this, where this is 2, here is 3. The minimum point here is 5/2 and negative 1/4. The endpoint, when x is 1, it is going to be bigger or equal to 1. When I substitute 1 into here, I'm going to get an output of 2. And when I substitute 4 into here, I'm also going to be getting an output of 2. So on the same horizontal line, I have the other point. This is a hollow dot. This will be 4, 2. And when I try to sketch the graph of y is equal to the modulus of x squared minus 5x plus 6, where x is supposed to be bigger or equal to 1, strictly less than 4, this portion will be reflected up. The other two portions, they are going to remain as they are. So my new graph, my final graph, in fact, which has this modulus, will be something that is like this. Okay, so this portion will remain, no change to this. So they're on the same horizontal line. This is going to be a solid dot, 1, 2. This is going to be at 2. This is going to be at 3. This is going to be a hollow dot. This will be 4, 2. And this portion will be reflected up. So my graph can look something that is like this, where this point here, the highest possible point, the maximum point is going to be 5/2 and positive 1/4. From negative 1/4, it becomes positive 1/4. And the range of values for y will be, it is bigger or equal to 0. And the maximum possible y can go, although this is a solid dot and this is a hollow dot, but this produces an output of 2. So the highest possible it can go will consist of 2. So y is going to be between 0 and 2, inclusive of 0, inclusive of 2. Let's take a look at another question. Let's take a look at C. In part C, we are going to try to sketch another modulus function that is involved in a graph, and it is still a quadratic function that we are looking at. And y is equal to x squared plus x minus 2 is what I'm going to try to sketch first. Factorizing this, this is equal to x plus 2, x minus 1. And the range of values of x that I'm going to be working on will be bigger or equal to 2, less than or equal to 2. Let me sketch the quadratic function first. It is a smiley face because the coefficient of x squared is positive, and it will look something like this. Okay, this is the quadratic function. It is going to be at minus 2, 1. So this is actually one of the endpoints. In fact, it is going to be a solid dot here because it can be equal to. The minimum possible point here is minus 1 over 2 and minus 9 over 4. Letting x be equal to 0, this point here is going to be equal to negative 2. Letting x be equal to 2, substituting inside here, I'm going to be getting this as 2, 4. So now I'm going to try to sketch this again, but with a modulus function. So y is equal to the modulus of x squared plus x minus 2, where x is supposed to be bigger or equal to minus 2, less than or equal to 2, will look like this. So here we have a y-axis. Here we have our x-axis, which I think I'm going to extend it a little bit more, okay? So for this here, x-axis, which is a slightly extended one, it is going to be, this portion will remain the same. So we will have this. And here is going to be at 1. Here is going to be a solid dot at 2, 4. This is going to be reflected. And it will give me something that is like this. Here, coming back down. This is going to be a solid dot that is at minus 2. This point here, the maximum point will be half, and negative half, and positive 9 over 4. And here is from negative 2, it will become a positive 2. Okay, and if you are warm up enough, let's just try a graph that is not exactly difficult, but a little bit more tedious. Okay, it requires us to go through a few more steps, which is in part D. So in part D, we are going to try to sketch the graph of y is equal to modulus of 4x plus 2 minus 3. And the minus 3 exists outside the modulus function. So what I'm going to first do is to sketch the graph of y is equal to 4x plus 2 without the modulus, without the negative 3, where x is supposed to be bigger or equal to negative 3 and less than 3. This is a linear line. It is pretty easy to sketch. Let me just do a quick sketch of it now. So we have this y-axis, x-axis. It is going to look something like this. Here is the y-intercept. Here is going to be positive 2. The x-intercept is going to be negative 1 over 2. It is bigger or equal to negative 3, strictly less than 3. So I'm going to use a hollow dot here. Let me just make it clearer that I'm using a hollow dot. So here, I'm using a hollow dot. So when x is equal to negative 3, if I were to substitute into here, I'm going to be getting this as negative 10. As for this 3 substituted into here, it will be 12 plus 4. This is going to be, 12 plus 2. This is going to be equal to 14. So this is my graph of y is equal to 4x plus 2. Modulus of this portion is going to be reflected up. Okay, so the next graph I'm going to sketch is y is equal to the modulus of 4x plus 2, where x is bigger or equal to minus 3 less than 3. So this portion is going to be reflected up. The other portion is going to remain as it is. So my graph is going to look something like this. Okay, this portion will remain. So we will have this hollow dot here. Here is minus half. Here is 2. Here is going to be 3 and 14. This portion is going to be reflected up. So we are going to have something that is like this. Okay, it is going to be a solid dot. The x coordinate is minus 3. The y coordinate is from negative 10. It is now going to be positive 10. So positive 10, it has to be higher than 2. It has to be lower than 14. So I'm trying to draw this point like somewhere in between here. So, but this is still not the final graph because my final graph has to be this and minus 3. So let's draw our final graph. Y is equal to modulus of 4x plus 2 minus 3, where x is supposed to be bigger or equal to minus 3 and strictly less than 3. So this minus 3 will cause the entire graph to be translated by 3 units in the negative y direction. It's going to be translated downwards. So let's shift this entire graph down by 3 units. My final graph will look something like this. Okay, this is the x-axis. This will be the y-axis. The entire graph is shifted down, right? So if the entire graph is shifted down, this point here, 2 minus 3 is going to be at minus 1. So my graph will be something like this. Okay, here it will be at minus 1 as we discussed. So this point here, it was previously minus half 0. So now at the point here, it is going to be minus half and minus 3. And it will be coming back up here. So here is going to be this point here, where the x coordinate is 3, the y coordinate will be 14 minus 3. It is going to be 11. Then this point here will be somewhere here. It is going to be minus 3, and 10 minus 3 is going to be equal to 7. So I have this, but we will still need to indicate this point and this point, the coordinates of these 2 points, which I don't have. And I think if we want to, we can either use our graphing calculator to find these 2 points. In fact, we can even use our graphing calculator to sketch this. But since we are doing this entirely, like manually, let's try to solve for the roots of this equation, shall we? If I were to solve for the roots of this equation, we are going to be letting the modulus of 4x plus 2 minus 3 be equal to 0. Now we form our own equation. Let's see whether we can still remember how to solve it. So modulus of 4x plus 2 is equal to 3, which means that 4x plus 2 is going to be equal to 3, or negative 4x plus 2 is equal to 3. We have 2 possible scenarios. Solving for x for this. Let's see, solving for x, I'm going to get a 1/4. Solving for x, I'm going to get a minus 5 over 4. So this is going to be minus 5 over 4. And this here is going to be equal to 1/4. And what we have now is the graph of y is equal to modulus of 4x plus 2 minus 3.